Thank you for coming. My name is Andrew Lessier, and today we are presenting orientation stabilization in a bio-inspired bat robot using integrated mechanical intelligence and control. This work was done by Eric Sahite, Andrew Lessier, Pravin Dangle, Akshat Singhal, and Alireza Ramazani. We are all members of the Silicon Synapse Laboratory at Northeastern University.
The contribution of micro-aerial vehicles to monitoring and inspecting confined spaces has remained very limited. Our primary objective is to create a design framework for the design and control of aerial robots, inspired by birds and bats for their energy efficiency and agility. However, there are challenges. Such complex locomotion styles involve highly articulated joint mechanisms. For instance, bats can mobilize as many as 40 joints during a single wing beat. Additionally, such lightweight platforms leave little room for high-density actuation and computational power.
Traditionally, confined spaces are inspected with ground robots, which are extremely expensive and hard to operate. Micro-aerial vehicles are faster and cheaper than ground vehicles, but drones suffer from ground effects caused by their powerful air jets and are very fragile against impact. Although some platforms, such as Helios by Flyability, mitigate the impact resistance issue, quadrotors cannot escape instability caused by ground effects. As the space they are traversing gets smaller and smaller, these systems become increasingly unstable. Bio-inspired designs do not produce such air jets, and therefore, these solutions look very attractive for flight inside confined spaces. However, none of these works truly capture the flight characteristics of birds and bats because they are designed based on insect flight dynamics.
Widely used paradigms based on insect flight have failed to copy animal flight because they assume only closed-loop feedback roles and ignore computational roles carried out by morphology. For instance, here, the insect flight dynamics can easily be described with nonlinear time-periodic problems. This can be further simplified based on the averaging theorem. This can be done because insects have lightweight wings and their flapping cycles are extremely fast, which yields a 2-timescale system. Unfortunately, insect flight dynamics have been used to describe other forms of aerial locomotion, even though insect flight characteristics are not scalable.
To better understand vertebrate flyers, we are developing an aerial robot called Aerobat at Northeastern University, which is a flapping wing robot inspired from bats. This robot has a wingspan of 30 centimeters, and we designed it to have a total weight of 20 grams. The robotic bat arm wing is a mechanical structure with computational roles designed to mimic the flying maneuvers of biological bats. We also refer to this structure as a kinetic sculpture, where we fabricated it monolithically using rigid and flexible polyjet 3D printing materials. This rigid and compliant structure is designed to be actuated by a single motor and allow the wings to dynamically morph as they flap. The computational roles of this structure are actively modulated using closed-loop feedback, as will be discussed later in this presentation.
In contrast with other flying vertebrates, bats have an extremely articulated musculoskeletal system and deliver an impressively adaptive and multimodal locomotion behavior. There are over 40 active and passive degrees of freedom involved in bat flight, and it is not feasible to actuate them all. In our approach, we augment open kinematic chains with static feedback and readout to emulate any conceivable computation on some analog input stream. We achieve this through morphological computation, where morphology itself can become a potential computational resource. The Passive Walking Robot by Collins is a good example of how morphology can be a computational resource, as a robot can walk stably even without an active controller. Kinetic sculptures are designed to capture two important modes in a bat's flight: plunging motion and elbow flexion and extension, which allow the wing to fold during the upstroke phase. By reducing negative lift and inertia during the upstroke, this allows the wing to translate faster, resulting in a highly efficient flapping gait. Figure 1 shows the simulated performance of this computational structure, analogous to a bat's wing conformations. Figure 2 shows the kinetic sculpture design used in this model. It possesses rigid and compliant components monolithically fabricated to reduce weight. Through mechanical intelligence, we can generate complex motions through simple actions that change the morphology. Through this example, we see the dynamic morphing characteristics of the wings are heavily tied to the kinetic sculpture, where small changes in the linkage parameters can generate large changes in the resulting gaits. These changes can be introduced with tiny, low-power actuators known as feedback-driven components. For instance, a prismatic joint can be used to change the linkage size of sensitive components.
Here we outline the dynamical model of the system as manipulated by the FDCs. The dynamics are composed of inertial dynamics contributions, joint inputs, and aerodynamic contributions. These non-negligible inertial effects come from the substantial weight of the wings as opposed to insect-inspired counterparts. We consider 4 FDC locations in the kinetic sculpture determined based on sensitivity analysis of the computational structure. We performed sensitivity analysis to determine the FDC placements by evaluating the resulting flapping trajectory from a small change in conformation parameters. Here we show the change in the elbow and wingtip trajectory as we change the linkage length parameters by increments of 2.5%. Green and red trajectories indicate positive and negative change in length, respectively. Case 1 has the FDC placed at the crank arm, which results in a fairly small change to the resulting flapping trajectory. Cases 2 and 3 have the FDCs placed within the 4-bar linkages, a highly sensitive area, which resulted in a greater change in the trajectory. This sensitivity analysis shows that a very small change in the kinetic sculpture morphology can result in a large change in the resulting flapping gait, and consequently the resulting aerodynamic forces. Hence, the role of feedback control is subsumed under mechanical intelligence. We can exploit this by placing the feedback-driven components at these sensitive locations, influence the aerodynamic forces, and design a feedback stabilizing controller to achieve longitudinal stability.
We developed a simulator for this robot by modeling the system using kinematic constraints, Euler-Lagrangian dynamic formulation, and quasi-steady aerodynamic model. We modeled each wing segment as a simple rectangular wing and evaluated the aerodynamic forces using blade element theory. The aerodynamic force center of pressure is defined at the quarter chord distance from the leading edge. In this simulation, we used the lift and drag coefficients developed by Sain and Dickinson. Now let's see how the kinetic sculpture's role is reflected in the vehicle flight dynamics and how they help reduce dimensionality of the control and actuation problem. The system dynamics, including computational structures, can be written in the following way. Here, XP only embodies the vehicle position, orientation, and passive coordinates due to compliance. YA denotes the aerodynamic contributions, while eta reflects the morphing dynamics governed by the computational structures. The dynamics of the kinetic sculptures can be presented in the following way, where the design parameters such as K denote compliance. The last subsystem is the state space representation of the fluid structure interactions. One last note, FDCs steer both inertial and aerodynamic contributions. This is the simulation of the closed-loop system, as the FDCs are used to regulate the longitudinal dynamics of the vehicle. Please note that the system is tailless, and as a result, the longitudinal dynamics are open-loop unstable. We first simulated the open-loop flight response of our system without using any controller or FDCs. The pitch slowly increases and will go unstable as time goes on. Next, we apply FDCs to stabilize the system. We used an optimization scheme to find the optimal gain value to stabilize the pitch dynamics. This cost function is used to find the optimal controller gain, K, by minimizing the body angular momentum, linear velocity, and pitch angle tracking error. This figure shows the simulation results of a closed-loop flight using the FDCs. As you can see, the pitch angle is stable near the pitch reference angle of 33 degrees. This shows that the Mimic framework not only can address dynamic morphing in high-dimensional systems such as Aerobat, but can also provide a solution to actively stabilize its flight dynamics which is open loop unstable. This figure shows the shoulder and elbow joint angle trajectories during the simulation, which was greatly influenced by the change in FDC lengths. The shift in FDC during the transient response greatly influences the resulting flapping gait. In this work, we presented a control framework using integrated mechanical intelligence and control. Unlike mainstream schools of thought, which completely ignore the role of morphology in aerial robot control, instead we subsumed the responsibility of feedback under computational structures. This allowed us to stabilize the otherwise unstable dynamics of Aerobat, while being able to copy dynamic wing morphing characteristics of bats. The feasibility of this control framework was shown through simulation. This concludes our presentation today. Thank you for listening and have a great day.